let's look at page 152 on internal energy. Have you heard of this internal energy before? Watch the Chinese movies? Then they have all the internal energy, right? Yeah. But it's not the same, lah, of course. In physics, internal energy, we will need to understand that it is made out of two components, okay? So just a quick overview first. This one on page 153. Internal energy. You have your internal potential energy as well as your internal kinetic energy. Okay, we have learned actually these two components also. So I'm going to choose people who were talking. Xiao Wei, can you tell me something about the internal kinetic energy? What do we know about it? Xiao Wei, come on, hurry up. Then Yang Kun will tell us something about the internal potential energy, because his back is facing me and I don't like that. Turn some more, Yang Kun. Turn some more. Hey, Xiao Wei, ready or not? Hello, internal kinetic energy. What do we learn in the previous chapter? How is it related to temperature? Yeah, so what have you learned in the previous chapters? Did we learn that the higher the temperature, the more they vibrate? That's right. Okay, and these particles, we actually learned that they are part of a model. What is that model called? Yes, it is related to a kinetic model of matter. Right? All the particles that are made of, all matter, including this book, including the water in your water bottles, the air around us, they are made out of particles that are in constant random motion. Okay? So that is our kinetic model of matter. Then we also learned in the previous chapter through what's that process where you heat up something, then the particles, they vibrate more, then they knock each other, knock. Conduction, right? So we also learned that the kinetic energy of particles are related to temperature. So the higher the temperature, the more they vibrate, isn't it? Okay, and what else do we know? Okay, Yang Kun is going to share with us something about the internal potential energy. Option of. Okay, quick recap again. Last time we talked about potential energy, right? The different types of potential energy. Do you remember what they are? Examples? Yes, GPE. What else? Elastic potential energy. What else? You also have your chemical, right? So this one over here, internal potential energy. What kind of potential energy do you think is this? What kind of potential energy? Sorry? Elastic? No. Yes, it will be chemical potential energy. We are talking about the bonds between the particles. Okay? So, like as mentioned in your textbook, there is stretching and compression of the interatomic or intermolecular bonds as the particles move. And there is also it's related to the forces between the particles. And over here, we are talking about the chemical potential energy. So this has got to do with forces between particles. And what do you remember for the forces between the particles? Which one is the strongest? Which phase has the strongest forces between particles? Solids. Solids have strongest forces. And how could we conclude that they are the strongest forces? Later on we will explore a little bit, okay? But generally we know that solids have a fixed shape, right? And they are held together by The particles are held in an orderly manner, held together by strong intermolecular forces. Okay, these are the forces we are talking about. For liquids, are the intermolecular forces as strong? No, they are slightly weaker. That is why they don't have a fixed shape. And finally, the phase that has the weakest intermolecular forces must be, gases have weakest intermolecular forces. Okay? Yes? Forces of? Or attractive force. Yeah, it's okay. In physics, we can use that. Okay? Then, so both concepts, they were already covered earlier on. They combine together to give us the term internal energy. Okay, so everything has internal energy. It's dependent on your kinetic energy as well as the forces between the particles. So basically what I'm saying is page 153, the top there is very important. Okay? So how do you give something internal energy? So what do they do in the movies? Yeah, like what Owen is doing, right? The Chinese old movie, they will do this, then what happens between the person's back and his palms? Sometimes you'll see like smoke and everything, right? They transfer the internal energy. Well, in physics, we also can we can cause an object to increase its internal energy. For example, this book. I can cause its internal energy to increase. What can I do with it? No, not throw. I heat it up. Maybe I put it inside boiling water. Then the temperature will increase, right? And when the temperature increases, then this part will increase. The kinetic energy increases, therefore internal energy increases. Okay? So just one example. Then your textbook also gives an analogy. Page 153. If you watch documentaries in the desert, the lizards, right? They're more active at warm temperatures than at cooler temperatures. So similarly, our objects, the particles, they vibrate more at higher temperatures as compared to lower temperatures. Right, Zafan? Right? If I can't see your eyes, then I'll be very suspicious. Especially if the book is just standing there by itself. Okay, put it down. Okay, put the book down. Okay, next part. Melting and solidification. 9.2. We are on page 154 now. When you talk about melting and solidification, what do you think about? What are some of the things you think about? Ice, okay. Ice melts. What else comes to mind? Okay, solids to liquid. So what is this process called? Solid to liquid? Melting. What else do we remember? Solids to gas, okay. Solids to gas, what is this called? Don't know how to spell, physics. I'm a physics teacher, I don't know how to spell. Okay, what else do you know? Liquids to solids. And what's this process called? Freezing. Any more? What else do you remember? Gas to liquid. Really? Gas to liquid. Is it part of this one? Part of these two? Any more? That's all you can remember? Okay. Probably this information that you recall from primary school. Okay? Sublimation, we are not going to cover this from solids to gas because we are only interested in melting and solidification. And as you have correctly pointed out, okay, instead of calling this freezing, we can also call it solidification. As you have correctly pointed out, solids to liquid is melting, liquids to solids is solidification. So these two processes, they are kind of the opposite of each other. Okay? They are the opposite of each other. And we see that in the most common example will be ice that is melting. Yes? Who? Damira is not here. Okay, focus back here. Hey, Zafan, why are you so interested? Okay, now, ice melting at room temperature. Does it only melt at room temperature? What temperature does ice melt at? How much? 0? Any temperature ice also can melt, is it? So what about negative 10? Above 0. What is the ice that will melt at negative 10? Is it? So it's not pure ice anymore. I'm talking about pure water. Okay, then we'll talk about that later. And then the opposite will be you freeze water. You put water inside your freezer. What temperature do you set in your freezer? Really? You set 0 degrees? You probably set negative something, right? Something that is lower than 0. And your water will turn to ice. Okay, so this topic we'll find out exactly what is happening. Okay, so let's talk about melting first. When a substance in a solid state changes to liquid state upon heating, the change of state is called melting. So for example, you take ice from the freezer, you put it out onto the table, room temperature. Are you adding a source of heat? Are you introducing a source of heat to the ice? Yes or no? When you bring it out to room temperature. Yes, you are. The source of heat is the environment. Because the environment has a higher temperature of 20-something, 30-something degrees. As compared to the ice, which when you take it out, what is the temperature of the ice? What's the temperature of ice when you take it out? 0 or lower? 0 or lower? Okay, you all don't know the answer here, okay? Later on, hopefully by the end of this lesson, you'll know. Then there's a source of heat. Then it will start to melt. When the ice melts, it has a particular temperature, and that temperature is called the melting point. Okay, if you didn't catch what I said, I'll repeat it because it is very important. The particular temperature at which ice melts is called the melting point. Can? That is found in page 154, your first paragraph. So, do you think I will find a piece of ice that is at 2 degrees Celsius? Possible or not? Harith, possible? And I have ice, meaning solid H2O at 2 degrees Celsius. Hang on, let Harith think about it, the rest can also think. Possible or not? What's the answer? What? Ice, I don't care half an ice, whole ice or not. Yeah, okay, it is not possible. Because ice has melting point of 0 degrees Celsius. So when you take ice out from the freezer, out into room temperature, it is at 0 degrees Celsius. It is not at negative degrees. It is not at negative temperatures. It is not at positive temperature. It is at 0. So when you take it out, right, your ice is starting to melt, right? Right, Zafan? Ice melting, right? You put it on the table. What temperature is it? How much? 0. The temperature of this, as it is melting, temperature equals to 0 degrees Celsius. It will stay at 0 degrees Celsius until the whole thing melts. Okay? Because why is it melting? It is absorbing heat from the surroundings. Then, as it is absorbing heat, what happens to its internal energy? As it is absorbing heat, what happens to the internal energy? It increases. Which part increases? Is it the internal potential increase or the internal kinetic increase? Sure? So you're telling me it's kinetic, huh? But what do you remember? What do you all say just now about kinetic? It's got to do with temperature, right? Then, when it is melting, did the temperature change? When it is melting, did the temperature change? One more time, huh? When it is melting, does the temperature change? No, it stays at 0 degrees Celsius. So when it stays at 0 degrees Celsius, temperature doesn't change. Can your kinetic energy change? Cannot. So, but we also know for a fact that internal energy increases. So which part contributes to the increase in energy? So you see, this one increases. This is constant. So what must have changed? Which one must have changed? Internal potential energy, isn't it? Because internal potential energy plus internal kinetic energy gives you internal energy. If this didn't change, then this must change. This must increase for your internal energy to increase. Can follow the logic? Okay, so what does it mean when our internal potential energy changes? When this changes, the forces, we are talking about forces between the particles. And we know that solids have strong forces. And gases, they have weak forces. You are gaining energy, and this energy causes the forces to be weaker. You give it energy, you break the forces. So when the forces break, they change state from solid to liquid. Okay? To break a force, you need to supply energy. We are supplying energy in the form of heat to weaken these forces such that the solid, they no longer have very strong intermolecular forces. They are weaker now, and the particles are no longer held in a fixed shape, which is shown by melting. Okay, they change the state from solid to liquid. Who don't understand what I'm talking about? Or who has an idea of what I'm talking about already? Anybody has an idea of what I'm talking about? Only Afiq, Gaius, Myra, the rest don't know. Winnie Yong, do you know what I'm talking about? Then you now raise your hand. I want to have an idea of how much you have absorbed already. If you have absorbed enough, I can move on. So who knows what I'm talking about right now? Have an idea. Don't need to be super clear, but have an idea of how the molecules are related, the movement of the molecules, thank you, you can put your hands down, and the forces are related to the internal energy. Okay, thank you, Owen, put your hand down. So we can actually conduct an experiment in the lab on melting. Very simple experiment. So in page 154, you have a beaker of crushed ice, or the ice that's being crushed, and then you have a thermometer. We expect the temperature inside this beaker to be 0 degrees Celsius, right? As ice is melting, it should be 0 degrees Celsius. However, when, let's say I heat it up. When I heat it up, do we expect all the ice to immediately melt? No. It will melt at a higher rate. But while it is melting, what is the temperature? While it is melting, what is the temperature? It is still 0. Okay, so if we observe the temperature, if we plot out the temperature of the crushed ice, we will get what we see in page 155. Okay, you will get a curve where you see the temperature increase from negative to positive. When it is at Q, temperature is 0. Then it is flat. It stays constant from Q to R. What is happening over there? It is melting. The whole thing is melting. From Q to R, did they introduce the fire? No, then at which phase did they introduce the fire? They introduced it between Q to R. That is when it is melting. Because as it is melting, temperature stays constant. When does it melt? The moment you bring it out of the freezer. The moment you introduce the fire, it will start to melt. Okay? So between Q to R, there is the fire, there is a heat source, and it is melting. So they also gave you a diagram when it is in a solid state, meaning temperature is below 0 degrees Celsius, they are packed in an orderly fashion. When it is undergoing the process of melting, they did not show you the arrangement, but some of the particles, they are already slightly separated. Some of the bonds are broken because they have gained enough energy. So finally, when temperature rises above 0, the forces are now weaker and the particles are free to move about in the liquid. Okay, so when I give you a graph, let's say I'm not using ice this time. This is temperature in degrees Celsius, and I have time per seconds. And this is my substance. Okay, I tell you, this substance over here is being heated up. Okay? Tell me the melting point. Anqi, what's the melting point? How much? 10. Why do you all say it's 10? Because we are looking out for the region where it is constant. We are looking for a region where there is constant temperature even though time is passing. Okay? At this part, temperature is constant. Therefore, we know there is a change in state. And because I tell you that this item is being heated up, it is melting, I want the melting point, this has to be it. Okay? Meaning, anytime I give this kind of graph, whatever item is it, whenever it undergoes the process of melting, temperature is expected to increase. Then when it is melting, it will be a constant temperature. After it has finished melting, then the temperature will rise again. Yes? To wash your face, is it? Yeah, take the pass and tuck in your t-shirt before you go out of the classroom. Alright, so that's all. We move on now to page 156. What happens when a solid melts? So the misconception that many students have is that when the solid melts, the temperature increases. That is a misconception. So please don't write those kind of things. When the solid melts, the temperature is supposed to be constant. It is constant. And that is how we identify the melting point. Can you imagine if I give you a graph of an object that is like that, temperature and time. Ask you what's the melting point. Can you identify the melting point? You cannot. There's no flat horizontal region for us to identify the change in a phase. Okay, so no melting point over here. Instead, what is happening is the temperature is just rising. For example, water is being heated up. So from a temperature of maybe 3 degrees Celsius, we see that the temperature of water is heated up. And it remains as a liquid. No change in state because no flat regions. Okay, then at this point in the graph, the highlighted portion, I mentioned that it is changing its state, melting. And it is still gaining internal energy. At the yellow part, gain in internal energy. Since the kinetic energy is not increasing, then we know that energy is used to break strong bonds. Okay, because the energy is not used to give the particles extra kinetic energy. How do we know that? This is because there is no change in temperature. See the repetition? I keep repeating the same point. No change in temperature, no change in kinetic energy. Alright? But since there is an increase in internal energy, therefore the increase must come from the internal potential energy, which is related to the strong bonds. Then you need to be able to express all these in words. Okay? Then the opposite that happens will be solidification. Solidification is just the opposite from liquid to a solid. So right now, what I need to imagine is putting water in a freezer. While it is still in its liquid state, the temperature could have been maybe 3, maybe 5, maybe 10 degrees Celsius. But as you put it in a freezer, temperature starts to drop and drop and drop. When it is at 1 degree Celsius, what is the state? H2O at 1 degree Celsius. What is the state? Okay, liquid. What about at 0.5 degrees Celsius? Still liquid. At 0.001 degrees Celsius? Okay. When it goes down to 0 degrees Celsius, what is this state now? What is this state? Solid or liquid? Solid plus liquid. In fact, I don't even want to tell you what state it is. I will just say this is solidification or freezing point. Okay? And this temperature, it starts to freeze. So if I draw the graph, what will it look like? Temperature initially would have been above. It would have been above 0. So temperature is going to drop. Maybe let's say this is 10, okay? It starts to drop. Then when it comes down to 0, what happens? Continue to drop? Do you think it continues to drop? If, let's see, going by our logic, over here is still water, right? Right? Then if it continues to drop at 0, then over here, solid. How long did it take to change from liquid to solid? According to this graph, instantaneous. The moment it dropped to 0 degrees Celsius, the whole thing becomes ice. Is that the fact? Do we see that happening? No, we don't. Instead, what happens is at 0 degrees Celsius, it takes some time for all the liquid to convert to solid. So we don't have this. Instead, what we have will be one flat region again. And then it goes down, the temperature drops again. So what happens at this flat part? This is a change in state. So like I said, every time you see a flat region, it is a change in state. And it is up to you to tell me what is this process called. Obviously, since we are talking about ice freezing, this will be called solidification. And this over here, 0 degrees Celsius, is my freezing point. Okay? So, can you tell me what is the freezing point of water? 0 what? 0 degrees Celsius. Can you tell me what is the melting point of ice? 0 degrees Celsius. So at this temperature, your solid phase, meaning your ice, and liquid phase, meaning your liquid water, they coexist. You have some solid, you have some liquid. And it is only when they have completely changed into either the solid state or the liquid state that we have a change in temperature again. Otherwise, your temperature stays the same. Okay? So the graph of a different substance that is undergoing solidification could be as such. It's time and temperature. So let's say this is 85, this is 70, and this is 0. What is my freezing point for this substance? We look at this flat region. This we identify as having a change in state, which is known as freezing. So therefore, freezing point equals to 70 degrees Celsius. Any questions? Okay. Then subsequently, 9.3 will be on boiling. I'll try to bring you all to the physics lab. We will see for ourselves that the temperature is really constant when it is undergoing a change in state. Okay? Then we try to learn a bit more. Right now, freezing, because it requires a freezer, which I don't think the lab has, so I didn't show it for freezing and melting. But we will see that for boiling, okay? So if there are no further questions, there is